So now we are moving one layer down. This is top down. So we finished the applications and we are in layer 4. In layer 4, we will first talk about things which are independent of TCP or UDP. So any transport layer protocol should provide multiplexing, flow control, error control, optional, well basically may provide, let me put it this way, not must provide. It may provide multiplexing, demultiplexing, flow control, error controls. We talk about that. Then we see what UDP provides, what TCP provides. In each case, we talk about the header format, connection management, and so on and so forth. So first, the discussion here is independent of TCP and UDP. And we will talk about the same things as you said, multiplexing, flow control, error control, etc. And all of this discussion is for the transport layer, which is layer 4. So, since it is layer 4, there are devices that are not involved at all. So when you have an application, it goes from application to transport to the network to data link to physical layer, then it goes to a router. The router does not implement transport. We say that the router is a layer 3 device, so it only looks up to layer 3 headers and then forwards the packet to another router, it goes to many routers. They don't look at the transport layer. They just look up to the layer 3. Once it reaches the final destination, there the packet goes beyond the network layer to the transport layer again, and then it goes to the right application. Okay? So the key summary is the transport is end to end. Alright, the routers don't look at the transport, and it is not required for intermediate hops. So it is only, this is basically transport is end to end. So what are the things that the transport may provide? First thing they could do is multiplexing and demultiplexing. Multiplexing means multiple applications can use the same transport, and they can be used at the other end in the opposite direction. Error detection. Second thing the transport do is they may detect the errors. So if any bits gets changed anywhere along the path, they will know it. They can detect the loss. If any packets get lost, they will know it. And the packets do get lost along the way, simply because if lots of packets come to a router at the same time, it may run out of memory and may not be able to receive some packets, so they will be just lost. Buffer overflow. And it may also provide recovery from these two things. So if some packet is in error, it can ask for a second copy of that packet. If packet is lost, it can ask for a second copy of that packet, retransmissions. Flow control. It can make sure that the rate at which the packets are coming is the rate at which it can receive and not any more. Flow control. And we will actually have more detail on each of these coming up. Congestion control. It can ensure that the network has the capacity. So we divide the problem into two parts. Flow control is end to end, which means that the receiver has the capacity. Suppose you want to send somebody 2000 packets. We have to make sure that the receiver can receive 2000 packets, right? But we also have to make sure that the network routers can have the capacity to carry 2000 packets. So the second part is called congestion control. The first part is called flow control. Flow control is making sure that the receiver has the capacity, and the congestion control is making sure that the network has the capacity. Okay? Receiver and the network. So multiplexing and demultiplexing, how is it done? Obviously it is done by the port number, we have already talked about it. So let's say there are two users and one server. This user is talking to the server and this user is talking to the server. And just for the sake of it, we have two different servers here. We have a web server and a DNS server on the same computer. So this user is talking web and this user is talking DNS, or both, they could both be talking web, it doesn't matter. each application has a port number, right? That is the TCP address as we say it. So web has port number what? 80. And the DNS has some port number, which in this case it says, it doesn't say actually port number here. So anyway, it doesn't matter. So basically when it sends a request to the server, the destination port has to be 80 in the request. So the destination port is 80, the destination address is this address, the source address is this address, and the source port is any number. So the source port is not standardized. You can use any number for the source port for any application. Obviously that number has to be more than 1024 because all the standardized ports are below 1024. Right? You have port number like 465 for mail, 995 for secure mail and all that. So the numbers, all those standard numbers are below 1024. And above 1024 there are no standard numbers. So 3009 is a good source port number. When the message goes from here, it has the source address, destination port, and source port. It goes this way, means it goes from here to there. There the TCP knows that it is going to destination port 80, so it gives it to the web server. When the response comes back, what happens? These fields are interchanged. Source address becomes the destination address, and the destination becomes the source address. The destination port becomes the source port, and the source port becomes the destination port. Right? When the response comes back from the web server, it says it is going from 209 to 128. I am coming from port 80 and I am going to port 309. So there is no confusion as to which application is going to get it. This TCP module is used by all the applications. Right? There could be, for example, 5 web sessions going on. Right? You could be having Internet Explorer, you could be having Firefox, you could be having everything, right? They're all talking to port 80 here. So this one, TCP assigns a different port number to each application. The question is, why would you want to keep different applications on the same port? There are no applications which are on the same port. Only one application per port. Destination port 80. Source port will be different. Browsers are not using source port 80, they are using destination port 80. And if you have 2 web servers running, you can run 2 web servers. I think I gave you an example. You can run 2 web servers on a computer. They will use different port numbers. They will use port 80 and 81, and for people who are sending it, they will have to decide whether to send to 80 or 81. So you are allowed to put ::81. So TCP is a process which keeps track of all the ports used and unused. It just picks up so when the browser says, okay, here's what browser says, I want to send this message to this server on port 80. It doesn't put the source port number. It gives to the TCP module. TCP module knows the source port number. It creates a source port number and puts into that message. This is all software. There is no hardware required here. Basically, it just comes up with the number 3009 and puts it there. Now, this is all in the operating system. If you want to think about it, because TCP is an operating system module. It is implemented in Windows. It is implemented in OS X. TCP module is not. So it is an operating system. What if 2 machines use the same port number 3009? They are different IP addresses. You see, actually, let me just go back and one more time. Let me just say this. Each of these layers, lower layer supports multiple higher layers. So each transport supports multiple applications. Each network supports multiple transports. Each data link supports multiple IP addresses and so on and so forth. You could do that, right? So each transport supports multiple applications. So this is simply what we call the transport layer address. Port number is nothing but the transport layer address. Transport layer creates it and uses it to distinguish its client. So for example, I am the server, you guys are client, I would say you are number 1, you are number 2, number 3, number 4, and that's it. I can arbitrarily give you the numbers, and when the packets come and go, I know exactly where they have to go, and I don't have to ask anybody else. So TCP is, in this case, serving these clients, application clients, and create those numbers and arbitrarily select those numbers. Right? Alright. So now you understand how the port numbers are swapped, how the IP addresses are swapped. Okay, that's all about multiplexing, demultiplexing actually. So this allows TCP to serve many applications. Now again, it should be clear that there is not a TCP module per application. There is only one TCP module in the computer. There are many application processes running. They all talk to this TCP module. So now how do we detect the errors? Error detection is done by what we call CRC, cyclic redundancy check. However, CRC requires hardware. So we use in TCP, instead of CRC, we use something called checksum. CRC we will talk about when we come to Ethernet, layer 2. In layer 2 we use CRC. But in TCP we don't use CRC, we use checksum. And the checksum is very simple actually. Remember, it was designed back in 1974. And all it is one's complement sum of 16-bit words with overflow wrapped around. Now, there's a lot of words there. So you write down all the words in the message, all the words. Here I have given an example of 2 words, 16-bit and 16-bit. Most messages are much longer than that. So it doesn't matter how many words you have. So you just write down 16-bit, 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 16-bit. Whole message you write down. And then you create a sum. So 0 plus 1 is 1, 0, 1, 0 is 1, and 1, 1 is 0, and there is a carry. So this is not exclusive OR. This is a sum. And so there is a carry, and that goes to the next bit, and so on and so forth. At the end, you might get a carry here. If you get a carry there, then you bring it back and add it here. So this number plus this 1 gives you that value. Then at the end, you complement that value. So you send this value. Alright, so it is, now let me just read this again. One's complement of, so this is the value, so this is the one's complement of this value, of one's complement sum, and this is the one's complement sum, right? And what is the one's complement sum? One's complement sum is the sum with the carry wrapped around. Yeah, I mean if after this, and this is actually could happen, that this 1 becomes a 0 and there is another carry, we don't care. Yeah, you take all 16-bit words in the message, which includes the source address, destination address, blah blah blah. We'll come to that also in more detail later on as to which part is added. But you add up all those words and you do this. Yeah, so the comment was made that if there are 2 bits in error, maybe it will miss some of them. So yeah, it may miss some of the errors. Now, at the receiver, the opposite thing is done. All the words are written up, including the checksum, and they are added. If there is a bit, it is wrapped around, the sum is taken, and then the complement is taken. If you do everything right, this thing should be all zeros then. Understand? This is an exercise you can do yourself and verify that this is true for these 2 numbers at least, and obviously it would be true for other numbers. So at the receiver you will take 3 numbers, 1, 2 and the checksum, sum them up, wrap around, complement, the net result would be 0. A simple way to understand this probably is, and I haven't done this myself, but I'm just making it up on the spot, is that this is the sum and this is the negative of the sum. So if you put all that together, the total sum should be 0 at the end, So that is the kind of thing that is going on here. Is that at the receiver, you put the checksum also as a part of your thing. At the sender, this is what is done actually. At the sender, the checksum field starts out as all zeros. Right? You add up all the numbers, you do the complement and wrap around and whatnot, and whatever comes, you put that in the last 16 bit where you had all zeros. Right? At the receiver, you take the whole message all over again, and everything should come out as 0. So the algorithm is same at both places. All right, let's just see one's complement. 2's complement of 1 is, if 1 is 0, 0, 1, minus 1 is 15. 2 is 0, 1, 0, minus 2 is that, because you do the, this is the minus 2 representation, 2's complement. In 1's complement, negative of a number is direct complement. So 1 is 0, 0, 1, minus 1 is just the bitwise complement, and that is minus 1, minus 2, minus 3. 2's complement sum you add with a carry. 1's complement sum you add the carry back to the sum. So if you want to add 8 and 9, 8 is this number, 9 is this number. When you add them together, you get 1, you add that back and you get a 2. And complement of that would be 1, 1, 0, 1, which is minus 2. Alright? So, why they selected 1's complement and all that is because it is independent of the endianness of the machine. Now, what is endianness of the machine? It's almost like, sounds like Indianness, but it is endianness of the machine. And what is endianness? Basically, in the beginning, when we had computers, some companies decided that they will put the most significant bit first, and some companies decided that they will put the most significant bit last on the wire. So you want to send a number on the wire, where do you start? From this end or that end? Right? So the machine which put the least significant bit first, they call little endian. And the machine that put the most significant bit first called big endian. And that caused a lot of confusion when the little Indians have to talk to the big Indians as to how do they store all this information. So this operation, it looks like, is independent of which method you do, because it doesn't matter which end you start with. So let me explain. You could have byte endianness, you could have bit endianness. Okay? And so here I'm talking about the bit endianness. Now, so the point was raised that if you wanted to transmit a word consisting of 4 bytes, which byte do you send first? Right? Again, you have a choice, little or big. But I'm talking about sending a byte, which bit do you send first? Little or big? Right? So there is endianness at both ends, byte level endianness and the bit level. Now there was a question somewhere there, and I said I will answer. Is there a question still there? Anybody else has a question? No? Okay. All right. So the idea is, all you have to know is, if I give you words like this, the addition is all straightforward. There is not much difference between 2 and 1, whether it is 2's complement or 1's complement. The main difference is what you do with the final carry. And in 1's complement, we just bring it here, and so this number is actually a negative of that sum, and so that's why it adds up to 0. Okay? So you can do the calculation of the checksum.